Nope. 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 Okay, it is that time. So I am going to go ahead and get started. So in the lecture today, we picked up with the energy associated with a wavelength of light or a specific frequency of light. And that led us into our discussion associated with some observation that made us start questioning the atomic structure. Where are the electrons in the atom? Why do we have to expose the electron in an atom to a very specific wavelength if we want to completely eject that electron? And so we started talking about stuff like that, the photoelectric effect, the atomic spectrum. And those observations led to the Bohr model. And in the Bohr model, you had the nucleus surrounded by these orbits. The first orbit was right up against the nucleus, then the second orbit, then the third orbit. It would keep growing if we so desired. And we talked about the Rydberg-Balmer equation. The Rydberg-Balmer equation specifically explains, well, I should say mathematically explains the wavelengths of light we observed in the atomic spectrum. Now, the Bohr model is very useful from the perspective of simply getting a basic understanding of what's going on in the atom. Why did we inject it with a certain amount of energy to pop off an electron? Well, we had to completely get out of all of their orbits. Why did specific atomic lines show up in the spectrum? Well, that's because that electron would jump to a higher level and then fall back down. And as it fell back down, that atomic emission, it would give off a very specific color. So the Bohr model is really useful for just getting an understanding of what's going on. But the Bohr model, just like the Rydberg-Balmer equation, is really only accurate for hydrogen. Because once you get to helium, and especially once you get past helium, you have other things going on. Because once you get to helium, you have two protons acting on one electron and two protons acting on another electron. So plus those two electrons are going to be interacting, plus the two protons are going to be interacting. So there's a whole lot of extra interactions when you get to helium that weren't in hydrogen, which just had the one proton and the one electron. So that model that I showed you is the Bohr model. It's accurate for hydrogen, but it really doesn't work for any element past hydrogen because of other interactions that are present within the atom. So, continuing on our journey, we had people trying to figure out the mass of an electron or the speed of an electron, because you got to know those two things to know where an electron was. Well, the problem is you can't know the mass unless you cause the electron to stand still, and you can't know the speed if the electron is standing still. So an individual by the name of Heisenberg developed the Heisenberg uncertainty principle, which basically says we can't know the speed and the mass of an electron at the same time. We can't really know where an electron is at any given time, because we can't, if we know where it is, we've stopped it, therefore it's no longer in motion. So you got the Heisenberg uncertainty principle. And then another individual comes along named Schrodinger. and Schrodinger develops the Schrodinger equation. Now, I am not going to do the Schrodinger equation. The Schrodinger equation is calculus based. It is manageable by hand for hydrogen. But again, once you start getting into all those other interactions that you have to take into account in helium on, it quickly becomes too complex to solve the integrals associated with the Schrodinger equation. So instead of doing the Schrodinger equation, what I want to focus on are the quantum numbers that came out of the Schrodinger equation. These quantum numbers that I'm about to go over, basically, folks, they're like an address for an electron. Now, it's basically an expected address. So let me explain in a term that works. One of the quantum numbers is going to basically be like telling you what state it's in. So, or what state you're in. Let's use you. You start out with the word Arkansas. Well, that narrows it down. Then you narrow it down further by saying you're currently in Conway. Then you narrow it down further by saying you're in Manion Hall right now. These quantum numbers do the same thing for an electron. Now, I called it a suspected address because electrons are in constant motion. And while right now I can pinpoint your location, you're not going to stay there indefinitely. You're in constant motion, so you're going to be moving. It's going to change a little bit over time. So that's why it's a suspected address. So these quantum numbers that I'm going to be describing today is going to narrow down the possible location of our electrons. These quantum numbers, if you have done, how many of you have done electron configurations before? Some. These quantum numbers are directly related to those electron configurations. I can take quantum numbers and go to the electron configuration, or I can take an electron configuration and back it up to quantum numbers. They're related. So we're going to start out with the quantum numbers, and then on Tuesday, we're going to talk about electron configurations, and I'm going to back it up to the quantum numbers so that you start to put the two together. Okay. So our quantum numbers. The very first quantum number that we are going to deal with is going to be the principal quantum number. The principal quantum number is referred to with the letter N. Principal quantum number is a long set of words. So often we also call the principal quantum number as the shell. Now, the principal quantum number can be any whole number starting with 1 and continuing. And this number specifically describes how far away from the nucleus an electron resides. For a hydrogen atom, you've actually already seen this, even though I did not number it. The orbit closest to the nucleus would have been considered shell number 1. The next one out is shell number 2. The next one out would be shell number 3, and I could keep going. So it's describing how far from the nucleus an electron resides. Is it in the first shell away from the nucleus? Or is it in the second shell away from the nucleus? And so on. The next quantum number that we're going to deal with is the angular momentum quantum number. Which we represent with a lowercase l. Another name for the angular momentum quantum number is the subshell. An angular momentum quantum number can be any value within the range of 0 to n-1, where n is, again, the principal quantum number. Now, something to make note of, because it is important, especially when we move between quantum numbers and electron configurations. When the angular momentum quantum number L is equal to 0, that means that you are working with an S subshell. S subshells are spherical around the nucleus. When L comes out equal to 1, you're dealing with the P subshell. The P subshell is dumbbell in shape. With the center being the nucleus. When L is equal to 2, we're dealing with the D subshell. The D subshell is cloverleaf in shape, or I should say, to be more specific, 4 of the orbitals are. The other orbital
and we'll talk about the orbitals in a minute. The other orbital is going to be dumbbell with a donut. What that means is 4 of them will be somewhat like a 4-leaf clover with the nucleus in the middle. The one that is the oddball is dumbbell shape, but it has a donut that goes around it. The last one, when L is equal to 3, you will have an F subshell. And I can't draw those. I just can't. But I'll show it to you here in a minute. Now, folks, technically you can have an L is equal to 4, which would be called the G subshell. You can have an L equal to 5, which is going to be the H subshell, but we don't have any elements as of yet that have an L of 4 or 5. Right now, our elements end with an L of 3. So before I get to the picture that shows you all of them, the next thing I want to talk about is going to be the magnetic quantum number. The magnetic quantum number is M sub S. M sub L. Is the M sub L. The magnetic quantum number indicates the axis or axes, I don't know, the axis where the orbital resides on an XYZ coordinate plane. Now, the only way to know the exact M sub L value is to solve the Schrodinger equation. But there is information we can still get without doing it. And that is, first of all, the magnetic quantum number will be within the range of negative L to plus L. And the number of M sub L values indicates the number of orbitals. In a particular subshell. A valid set of quantum numbers follows the rules for quantum numbers. We're going to look at what that means in just a second, after I let everybody catch up with my writing. By the way, your quantum numbers are always written in the order of N, the principal, L, the angular momentum, M sub L, the magnetic, and another one we'll talk about in a minute, which is in a little bit, which is the M sub S. Folks, using my analogy, N is the state. L is the city. M sub L is the building. So that helps, if that helps at all. It's basically an address. Okay, so let's look at what I mean by following the rules. You have NL. Now, L had the rule, it had to be between 0 and N-1 if we're looking at a number line. M sub L has to be negative L to a plus L if we're looking at a number line. Actually, oh, no. Okay, so N, I said, had to be a whole number beginning with 1. So let's work with the 1. That means that our L value can be 0 to 1 minus 1, which is equal to 0. So if we're thinking about a number line, our only option here is the number 0. Our M sub L is a negative L, so a negative 0 to a plus 0. Negative L to a plus L. So in other words, again, it is simply 0. Applying all of our definitions. You have a 1, the electron is in the first orbital. Away from, or first shell, I meant, first shell. Away from the nucleus. In an S subshell, because M sub because L is equal to 0. And there is only one orbital. Because there's only one value for m sub L. Basically, folks, this particular one tells us that we have our nucleus in the first shell away from the nucleus. We have an S subshell. So that means it is spherical. And our electron is in that sphere. There is only one sphere because there's only one orbital. Questions about what it means and how it works? Yes. It helps once you get the rest of it together. Hopefully it's making some sense. But right now it's basically a bunch of numbers saying, oh, it's this far away from the nucleus. That's what N tells you. What does the shell look like? That's what L tells you. And how many of those are there? That's all it's really telling us right now. Okay, let's look at let's go a little further, and maybe as we go, it'll help. And part of the reason this gets a little bit more crazy is simply because a lot of people don't learn quantum numbers before they get here. But it is the way it all came to be. Okay, so first shell. Now let's look at the second shell. If it's the second shell, then our L value can be 0, 2, 2 minus 1, which is 1. So in other words, we have the options of 0 and 1 for our L value. The 0 is called an S subshell, and the 1 is called the P subshell. That goes back to the definitions I gave you earlier. Now your M sub L values. M sub L can be a negative L. So let's do each L individually. It can be a negative 0 to a plus 0 for the left-hand one. Or in other words, our only option is 0. But for the right-hand one, according to I'm following the rules that I have up there, the negative L, it can be a negative 1 to a plus 1 on a number line. So if you're looking at the number line on the left-hand side, it can be a negative 1, it can be a 0, and it can be a 1. So what we have is in the second shell, we have the S subshell, which has just one orbital because there's only one M sub L value. And we have a P subshell, which has 3 orbitals because there are 3 M sub L values. So if I were to draw this, folks, and go up to this point. Whoops, didn't want to do that. Here's my nucleus, and you're going to have, I will not go much further past this because it gets too crazy for me to draw after so far. You have your nucleus. Remember the one from previous, because they build on each other. So you don't do the two until you've done the one. You've got the one from previous. Now in our second shell, which I'm going to do in a different color to make it a little bit more obvious. You have a sphere. Around the nucleus. But also within that, in that same second shell, you also have the 3 p orbitals, which were dumbbell shaped. One on the x-axis or y or z, whichever direction you want to call whichever one. One on each of the 3 axes. That's what we're describing when we start describing these numbers. You had the 1, you had the 1s. That was our beginning. Then we went to the 2 for the principal quantum number, the second shell. And in that second shell, you had an s, which is the big circle, and you had the p, which are the 3 dumbbells. Questions? Yes. You are not going to have to draw anything. I give you pictures and ask questions, but as far as drawing, no. Now, folks, one thing I do want to point out is if you go back, I said in order for a set of numbers to be valid, what did I mean by that is what I want to describe next. What I mean is that it has to follow one of these paths. So it can be the 2, 0, 0. What it can't do is it cannot cross trees. So you can't go to the 1 and then cross over to this 0. It can't cross trees. In order for it to be valid, it has to follow the path outlined. If it does not follow the path outlined, it is not valid. Okay, what I want to do for a minute is I am going to give you a minute to do the next shell, which is shell number 3. I want you to develop quantum numbers aloud in shell number 3 based on the rules.
Okay, when you did so, you should have found with principal quantum number 3, our L can be any value from 0 to 3 minus 1, which is equal to 2. So it can be a 0, it can be a 1, and it can be a 2. Meaning in the third shell, whether we fill them or not, we don't have to fill them all the way up. But as soon as that third shell comes up, you have an S subshell, a P subshell, and a D subshell available. Now, for the S subshell, it has only one orbital, and it's going to be spherical. For the P subshell, it has 3 orbitals, so 3 dumbbells. For the D subshell, it has 5 orbitals because it has 5 Snell values. Questions about those numbers in there? Yes. Well, it's actually 4 clovers and a dumbbell with a donut. And if we could continue this, folks, we could do principal quantum number 4. And we could come up with, you would find out that as soon as that 4th shell opened up, you have 4 subshells, an S, a P, a D, and an F. Now you may not fill them all up front, but you have it. That's actually going to be important when we start talking on Tuesday. Maybe you don't have to fill them, but they are there. And so now there is one more quantum number, but it is a quantum number that was not part of the Schrodinger equation. The 4th quantum number is important when we get into multi-electron atoms. The 4th quantum number is the M sub S quantum number. I'm going to scroll down, but leave a little space because we're going to come back and fill it in. M sub S is referred to as the spin quantum number. The maximum number of electrons an orbital can hold is 2 electrons. The values for those 2 electrons is either going to be a +1/2 or a -1/2.
We're gonna have elements. We're gonna have elements that are really big. So how are we gonna only be able to have some
Per orbital. Remember, your orbital is the M sub L. So this orbital can have a +1/2 and a minus 1/2. Each of those 1/2s represent an electron. So there's two. This orbital can have a plus 1/2, minus 1/2, plus 1/2, minus 1/2, plus 1/2, minus 1/2. So there's 6 more. And these can all have plus and minus, which is 10 more. The plus and minus actually represent the electrons themselves. Yes. What now? No, it can only hold 6. Actually, and I saw everybody look at the periodic table, and it's something I'm going to explain on Tuesday again, but you're going to get a preview. How many can an S have? How many plus 1 minus 1s? 1/2. They can have 2. That is why this section of the periodic table is only 2 elements across. How many can the P's have? 6. That's why this part of the periodic table is 6 across. How many could the D have? That is why this part of the periodic table is 10 elements across. Guess how many the F can have? 14. The F can have 14. Because that's what the lanthanide and actinide are, is the F series. You're talking to quantum numbers. In fact, that's what I was going to tell you. As we progress into electron configurations, we'll be developing the electron configurations from the periodic table, and they're going to be directly related to those quantum numbers too. It's all going to coalesce into a common piece of knowledge, I hope, after we get to go over this some on Tuesday. Any questions? The only thing I wanted to do is show you one picture because you've seen my drawings. And while I thought I did pretty good today, they're not that great. So let me show you what it actually looks like. Don't laugh at my picture. I'm not an artist. Okay. So the S subshell had 1 n sub-L value. And it's spherical. It's that top one. That is an S orbital. The P subshell had 3 orbitals. They are dumbbell in shape. One of them is the PX because the dumbbell's on the x-axis. One of them is the PY because the dumbbell's on the y-axis, and one of them is the PZ because the dumbbell's on the z-axis. Now I'm not going to ask you which one's which. Don't worry about that. I'm just explaining that it's based on the axis. The third row is your D subshell. And if you'll recall, when L was equal to 2, we had 5 orbitals. 4 of them are kind of cloverleafish. Well, they are cloverleafs. 4 of them are cloverleafs. And then that one
And the one I didn't even bother to try is the F subshell. And the F subshell, as we just discussed, well, there's 14 elements across. Each orbital can have 2. So how many orbitals are in the F? There's 14 elements across. Each orbital can have 2. So take that number and divide by 2. 7. That's these 7. And there's no way I'm going to try to draw those. Those are the F orbitals. Guess what? Unless you just want to hang around with me.
But as far as new material, I'm done for today.